Hi, in this video, we want to take a look at using weights to correct imbalanced data. Okay, so we're in the situation that I need to build a probability model, so like logistic regression. So I want to model the probability that an event will or will not occur. All right, so and then we're in the situation where our sample does not reflect the population that we want to model. Okay, so there's going to be issues with this, that the probability models are going to reflect the data we put into it, not the population that we want to model. So remember, the models we build are about the data we use, not the population we're trying to target. So if the data that I have is not proportionately matching the population that I want to work on, then there's going to be problems. Now, if it's a little bit off, that's okay. It's not that big of a deal. But if it's severely off, then the model probabilities are going to be wrong. And what's the point of building a model if the probabilities are wrong, right? Okay, so we've got four major ways to handle this. Okay, first one is weights, and that is my preference if I can do that. Second one is to downsample. That is, I remove some, or I omit some of the observations from the overrepresented levels. We can upsample. Now here we take the underrepresented level and we basically double up on its data. We sample with replacement on the low frequency or the underrepresented level. And the last choice is synthetic data, which is my personal last choice, but it's a good tool in our tool belt if we don't have other options. Now, changing weights is not always an option. So for example, some models structures just don't accept weights. And if I'm going to be using one of those models, I can't use weights. So we'll have to use one of the other options. Also, if we have very, very few observations of a level, weights really are not going to fix that problem. We really need more data. Honestly, if I was in a position that like I had very, very few observations of a level, say I only have like 3, and I need to, build a model, I would honestly use synthetic data, probably do downsampling and change. I would use 3 of the 4 options I've got to tackle that. But weights by itself will not be sufficient. All right, so for this example, what we're going to do, first and foremost, I'm going to build a model that should give us probabilities of a good loan at about 98%. All right, so let's say a priori, in this example, I'm making the assumption that 2% of loans are bad. Or if 2% of loans are bad, then when I make a model with, let's say based off of gender or something, then I know that the overall rate of bad loans should be modeled at around 2%. And if I don't see that, then there's something wrong. The data that I have here as is will give me a bad loan rate of about 30%. 30%, huh? It's a lot bigger. Now, that might be acceptable if we adjust our cutoff for making decisions, but my point of view is that if I'm building a probability model, I want good probabilities, or I don't want to do this. Classification models don't suffer from this problem as much, but this is still an issue. So I like to have my output reflect the population that I know that I'm targeting. All right, so here I'm loading the data. It's the German credit data set from the Carrot package. And then this part is I'm building another column just for gender, male, female. And basically, I'm just using this just to make a very simple model to show you why this is important. Okay, so let's go ahead and let's build the model without changing any weights. So what I'm going to do is I'm going to say that the classification of the loan depends on gender and nothing else. Okay, and so overall, my probabilities should be about 0.98 on average. All right, because I know a priori that 2% of loans are bad. Well, what happens when I go through and I make a prediction based off of gender, we can see that this is modeling 65% of female loans will be bad, or sorry, 65% of female loans will be good, and 72% of loans to males will be good. This is much lower than 0.98. All right, so what would happen in this situation if I was using this model to decide, or if I use the data as is without making any adjustments, any probabilities that I get would be very, very pessimistic. All right, well, so what would end up happening is if I was a bank, if I was a loaning organization, I would end up not loaning money to people who would pay me back, and I would be losing clientele. Now you might say, hey, that's okay, I don't mind that, because I'm protecting my assets. Well, really, you want good probabilities. If you want good probabilities, because you can interpret it right, you can set the right criteria, you can understand why it is like you can understand what's going on. If you have a bad output, is it really a good model? So honestly, if I was to build a full model on this data, and then I was to rank the loan candidates off of the probabilities, it would probably be in the right order in terms of level of risk, but the probabilities would not be meaningful for this. So I don't like that. I want whatever I get as output, I want to be able to trust. Now, if I was doing a classification model where I just go, give them a loan, don't give them a loan, then I'm not so worried about this aspect as much, because there's a little bit more resistance to the imbalanced aspect. All right, so let's go ahead and let's make a bar plot just so I can show you what's going on. So if 98% of loans are good, the bar should be around here. And we can see that there's a pretty big difference. So let's go ahead and let's change observation weights. All right, so I know beforehand that about 2% of loans are bad, 98% of the loans are good. In my data set, I've got 30% are bad and 70% are good. All right, so if we sit down and we work out the mathematics of this, the way to adjust the weights in this manner is that I want all of the bad loans to account for 2% of the total weights, and I want all of the good loans to account for 98% of the weights. Okay, well, if we do a little bit of college algebra, we can work out that the ratio of the bad to good weights will be equal to the ratio of percent population bad divided by percent sample bad divided by the ratio of percent population good over percent of the sample that's good. All right, so I'm taking this ratio and it's like matching up to the bad weight, and then this ratio is matching up to the good weight. Now, something you'll notice is that when I work through this, it doesn't matter really what the total amount of the weights are when I pass it into regression within R. So as long as all the numbers are positive, basically everything's going to get kind of like rescaled, so that it doesn't matter what the actual values are. It just matters proportionally how big they are relative to each other. All right, so if you sit down, you do the college algebra on this, we'll see that good loans need to have 21 times as much influence as bad observations. Now, I want you to notice something about this. I have more good observations than bad observations. All right, if you look through a lot of the online documentation about unbalanced data, they talk about the cases where you have very few observations of a particular level. Here, I have 70% good, but that's not big enough. I need 98% good. So to get this to where I need it to be, it needs to be 21 times as much influence as a bad loan observation. Okay, so how I do this, I create a vector, I call it vector weights, and then I name it by the levels in my data set, and then I use I vectorize it. I use vector notation to establish what it's going to be. So every single time that the classification in the data set was good, it's grabbing 21. Every time that the classification was bad, it's grabbing the 1 in this. And then I go ahead and I rescale it. So that way everything adds up to 1, just so that it's a little bit easier to interpret what's going on. Yeah. All right, so now what I'm going to do to verify that I have it the way I want it, I'm going to go ahead, I'm going to add up all of the weights by class. So I'm going to take all of the times that the class is good, and I'm going to add up the weights. I'm going to take all the times that the classification is bad, I'm going to add up the weights. And we see that we get exactly what I wanted. Unfortunately, I'm not going to show the college algebra pencil and paper work on YouTube. I know you're disappointed. All right, so now I'm going to build the same model, but this time I'm going to include weights. So here, it's the same formula as before, so classification depends on gender. Now this is a very simple model, but I think this is a good way of showing you the importance of having data that reflects the population we want to make an inference on. And then we have the German credit. And remember, when I'm doing logistic regression, within GLM, I need to use the binomial family. If I wanted to use probit instead of logit, I would use parentheses and I would use probit inside the parentheses. And then here, this is the big change. I put German credit weights. And I get a warning message, and I checked it and I see nothing that indicates that there's going to be a problem with this. Adding the weights, it invoked this, made it so that the warning came up. Without having the weights, the warning did not come up. I looked, I didn't see any difference in the output, so I just kind of proceed. And so now, when I run predict on my weighted model, we see that for females, we get a little bit lower than 98% good loans, and for males, a little bit better than 98% good loans. That matches what I understand the distribution of good and bad loans to be. So I'm satisfied with this. I'm happy. And here's a bar plot just to show you the difference. Well, that's all I've got for you. Take care and goodbye.